We might think about now some, at least, theory about solutions of the incompressible Navier-Stokes equations. We might think now about what are the properties and results relative to these solutions. One important property might be involving the conservation of energy in particular. If we look at a computation of, say, the scalar product of u, that is the velocity, with the momentum equation of the Navier-Stokes equations, we can write 174 and 175. The u nabla u might be negative half of the integral of the divergence u squared dx will be 0. And nabla p u will define as negative p of divergence u is 0. We can then write this particular equation 176, where 1/2 of the normal derivative of u squared plus viscosity of nabla u will be 0. If we perform the integration with respect to time, this means that for all times from the initial solution at time 0, we just choose this, the solution will be associated with the initial u formally. And we can write 177, that 1/2 u squared plus viscosity of the integral u squared dt, just a dummy integration variable, will be 1/2 of u naught squared, where u naught is the initial velocity. This shows that in particular, that if we map t for u, it will thus be decreasing. This equality shows that the smoothing effect from the viscosity term will be that there's an initial amount of energy in the flow. And we know that from the conservation, energy always accretes, but mathematically we can see this through this simple combination of equations. The solutions for the incompressible flow cases will always instantaneously be smoother due to that diffusion or viscous type term that belongs to nabla u. Another really important property of the Navier-Stokes equations in incompressible form is the scalar invariance of the equations. For example, if we solve the Navier-Stokes equations for u for time t from 0 to capital T in any dimension, then for a particular positive value of lambda greater than 0, we can write this equation. It's invariant. This will show that for 0 to time lambda negative 2t in any dimension r, which will be rescaled by a lambda coefficient, we'll be able to see that these can be invariant and scaled. So what about the properties to solve the equations? One might say, given initial data u naught, there's a solution to the Navier-Stokes equations with this initial data, and is it unique? Obviously, this is one of the most important and fundamental questions in contemporary mathematics at the time of this video. We might also ask another fundamental question: does this solution exist globally? It might, in fact, exist locally, but does it exist everywhere in time and space? As I just mentioned, there's no complete or theory that's satisfactory to answer any of these three questions: the initial data, uniqueness, and does it exist globally in time? If the flow has one particular invariant direction, which we don't normally observe in nature, then we might say that it's known that the fundamental work from Leray in 1934, which we'll review later in this lecture series, that the equations will be well posed in the sense that for any finite energy initial data, there will be a unique global in-time solution within decreasing energy, and this is a very famous work. In 3 dimensions, the situation is much less clear, unfortunately. One can solve the equations uniquely and globally in time if the initial data is small enough. This very small value can be measured in a function space invariant under the scaling of the equations. If the data is very large, there are possibly non-unique global solutions of finite energy, bifurcations, if you will. These equations, in a sense, can be written as distributions, but the uniqueness and smoothness are known to hold only for a very short time. And perhaps this is why we see so many unique flows in nature.